Hello, renewed greetings from Portugal. My name is João Sobrinho. In this short talk, I will overview my and Miguel Ferreira's recent work on optimal path routing. Suppose we want to deliver a file across a network as quickly as possible. Suppose that we want to stream a video across a network with minimum delay at specified data rates. In both cases, the underlying optimal paths result from compromises between delay and bandwidth. Current routing protocols are unable to route data packets on such optimal paths. In general, current routing protocols route on optimal paths only if the relative valuation of path matrix that defines optimality is consistent with the operation that computes path matrix from link matrix. We were able to devise a procedure and design a routing protocol that allows optimal path routing for an arbitrary optimality criterion. We then realized that the procedure we devised paved the way for optimal path routing concurrently for multiple optimality criteria. Since the latter problem subsumes the former, it gives the title of the paper. Returning to our opening example, our protocols enable simultaneous simultaneous delivery of files and streaming of videos across a network on their respective optimal paths. Optimal paths, related algorithms and protocols, can be treated with generality with a routing algebra. A routing algebra consists of a set of attributes, a total order on attributes, and a binary extension operation on attributes. Attributes represent arbitrary performance metrics. The total order on attributes defines an optimality criterion. The optimal attribute of a set is the most preferred attribute of the set. And the optimal attribute from source to destination in a network is the optimal attribute among all path attributes from source to destination. The binary extension operation allows calculation of path attributes from link attributes. Routing protocols iterate extension and election operations on attributes, one link at a time, one node at a time. An election operation is such that it produces the optimal attribute of a set. I will focus on vectoring protocols, which instantiate a separate computation process per destination. For a given destination, nodes continually extend attributes advertised by out neighbors into candidate attributes, elect an attribute among the candidates, and advertise the elected attribute to in-neighbors. It is well known that vectoring protocols do not route data packets on optimal paths in general. The key property underlying optimal computations is isotonicity. The extension operation is isotone for the total order if B equals or is preferred to C implies that the extension of A with B equals or is preferred to the extension of A with C. An equivalent characterization of isotonicity states that the extension operation distributes over the election operation. Indeed, vectoring protocols route on optimal paths if isotonicity holds. If isotonicity does not hold, then vectoring protocols do not route on optimal paths in general. The problem is that many path metrics that we find in practice do not satisfy isotonicity. So what can we do? An idea is to reduce the total order such that isotonicity is satisfied in the reduced order. Reducing an order means declaring incomparable some pairs of attributes. Two attributes are incomparable if neither of the two is preferred to the other. Rigorously, an isotonic reduction is a partial order contained in the total order for which isotonicity is satisfied. So it's a partial order, meaning that pairs of attributes are incomparable. The larger the partial order, the better in terms of routing. It can be shown that every total order contains the largest isotonic reduction. So now we have partial orders. How do we deal with partial orders? We have to define suitable path problems and design appropriate routing protocols. In a partial order, the concept of dominant attribute generalizes that of optimal attribute. A dominant attribute of a set is such that no other attribute of the set is preferred to it. And the dominant attribute from a source to a destination in a network is a dominant attribute among all path attributes from source to destination. The set of dominant attributes from source to destination is a set of pairwise incomparable attributes. And now we were able to design partial order vectoring protocols. These protocols also perform iterations of extension and deletion operations, but not on single attributes, but on sets of attributes. And we could show that if isotonicity holds for the partial order, then partial order vectoring protocols are able to route on the dominant paths. Importantly, if the partial order is a reduction of some original total order, then the original optimal attribute is found among the dominant attributes. So if we have a partial order vectoring protocol that routes on dominant paths, we are able to find the optimal paths contained in the dominant paths and route on the optimal paths. We are one step away from being able to route concurrently on multiple optimality criteria. Each criterion is represented by a total order on attributes, and what we do is just perform the intersection of all criteria. If that intersection satisfies isotonicity, we are done. If it does not satisfy isotonicity, we take the largest isotonic reduction. So we arrive at a partial order that is contained in all the total orders. Now we can use a partial order vectoring protocol, find the dominant attributes and dominant paths, and the original optimal attributes and paths are among those dominant attributes and paths. So that's the main ideas of the paper. The initial reviews of the paper prompt to clarifications. Routing data packets aside, one reviewer referred to the problems we addressed in the paper as multi-objective path problems. Multi-objective path problems are a special case of our framework. In these problems, attributes are tuples, each term having an associated extension operation and total order. And the extension operation on tuples is the product of the elementary extension operations, and tuples are partially ordered by the product order on the elementary total orders. Our framework is more general. Attributes are not necessarily tuples of elementary matrix. The extension operation is not necessarily the product of elementary extension operations. And the largest isotonic reduction and intersection of total orders did not necessarily lead to product orders. In fact, the paper presents the quickest path order on pairs with length, which is such that its largest isotonic reduction is larger and thus different from the product order on pairs with length. Another reviewer asked, why don't we use linked state protocols instead? I guess the assumption underlying this question is that computing optimal paths is somewhat easier in linked state protocols because every node has knowledge of the topology of the network. Linked state protocols use Dijkstra's algorithm to compute paths from a source to every node in the network. However, without isotonicity, Dijkstra's algorithm does not compute optimal paths. The concepts of largest isotonic reduction and intersection of total orders are as relevant to linked state protocols as they are to vectoring protocols. One of the reasons for our preference for vectoring protocols is because these protocols compute attributes from the destination towards the sources, allowing simultaneous installation of forward information to guide data packets from sources to destinations. And this is not the case with linked state protocols. I will end this short overview with a breakdown of the contributions. We presented two problems: optimal path routing for an arbitrary optimality criterion and optimal path routing for multiple optimality criterion. In the process of developing solutions to these problems, we introduced two new concepts to routing: largest isotonic reduction over total order or partial order, and intersection of total order or partial orders. Both concepts lead to partial orders. A central piece of our work was the design of partial order vectoring protocols that route on dominant paths and thus enable routing on multiple optimal paths. Thank you for listening. Your feedback is welcome. Please get in touch. Thank you. Thank you for listening. Your feedback is welcome. Please get in touch. Thank you.
Great talk, really impressive work. I have some wonderful questions coming in through Slack. So let's start off. So Sanjay Rao from Purdue asks, what do you think might be a simply naive question, but I think a lot of folks would really benefit from hearing from you, which is, could you provide an example where isotonicity is satisfied and one where it's not?
Okay, thank you. That's a great question to start, because many people may have that question. So isotonicity is satisfied, for instance, in shortest path routing. So isotonicity means that a local decision that I make for everybody. It's global as well. So what I like is what my neighbor will like as well. I can discard already paths that I know will not be good for anybody. So an example where isotonicity holds is shortest path routing. And an example where it does not hold could be shortest widest path routing, where you're trying to route on the shortest of the widest paths. So the first criterion is widest, and then you have the shortest among them. Or more generally, if you want to deliver a file, the best path to deliver a file is a combination of delay and inverse bandwidth or in inverse capacity. And this thing does not satisfy isotonicity. I don't know if that's sufficiently clear. I'd be happy to continue.
I think so. So Tim Griffin from Cambridge asks, what is the bound on the number of routes generated to any given destination? And Aditya Kella from Wisconsin, as a sort of follow-up with maybe kind of ties these questions together, is what's the complexity of the approach? How easy is it to realize this on routers today? So if you want to speak in general to the complexity on both sides.
Sure. It's an excellent question again. So there are cases where the number of dominant attributes that you have to collect at a node may be, in the worst case, exponential. So for instance, if you have two unbounded lengths, you can contrive a very contrived network, is really a very contrived network, where the number is exponential. Now, if one of the components that make up the attribute is, for instance, width, the number of widths in a network is limited, and so it can be polynomial time, it's polynomial on the size of the network. And the simulations that we did, we realized that what we really measure is much smaller than the worst case bound on the topologies and the metrics that we assumed. But there is an interesting aspect I would like to add, which is one of the protocols in particular, called non-restarting protocol in the paper, allows you to tune between optimality and complexity. So you can say, I accept a maximum of 3 routes in each node for a given destination. I'll lose perhaps optimality a bit, but I perhaps do better than electing just one. So what this thing does in a certain way is it breaks away from our prison of having routing protocols electing only one route per destination. I'm not listening, sorry.
Oops, I just hit something to somebody. I don't know what I did. I apologize, but I will just, to follow up, so Tim had a sort of follow-up question. You introduced the notion of K quickest paths and W wide shortest paths. Does each router have to use the same value of K and W? No,
by no means. So you can see the election of optimal paths in 2 steps. The network as a whole computes dominant paths. So you can see it the other way, which is the network as a whole discards paths that certainly will not be optimal for anybody. And then it gives a set of dominant attributes for every source to a destination. And then the source selects the optimal path among those attributes. It will be there. The optimal path will be one of those. So you just make the calculation of the quickest for the value of K that you want, and you choose which is the appropriate one.
Fantastic. Well, thank you so much.
Okay, thank you, João, for that interesting presentation. Hello, Miguel. So could you give an example for our listeners that maybe haven't looked at the paper yet? Can you give an example of a isotonic order and a non-isotonic order, just so people have idea of what we're talking about.
Yeah, of course. So I guess the most standard example for an order which satisfies isotonicity is our shortest paths. So attributes are lengths extended with addition, and the total order is just less than equal order. So shortest path routing satisfies isotonicity. So on the other hand, I guess from the examples we give in the paper, why the shortest path routing? Shortest widest path routing. So meaning that we first choose the widest path, and then the shortest among the widest does not satisfy this property. I guess for another example, a more less trivial one, we can think of quickest path. So the quickest path is the order underlying the time to propagate a file across a network, and this order as well does not satisfy isotonicity.
I see. Okay, thank you. I have another question. So, you know, when we think about policy-rich protocols like BGP, right? It seems to me that, you know, this difference between local optima, let's say kind of a Nash equilibrium, you get the best thing given what your neighbors give you, versus global optimality. It seems to me that with a protocol like BGP, that actually the local optima is exactly what we want, because we don't necessarily, the notion of global optimality doesn't even make sense necessarily in that case. And in that case, your largest, what do you call it? The largest isotonic
reduction, yeah.
Yeah, it's going to be something trivial like the equality relation, right? So can you talk about that a little bit?
Well, so first off, I guess that our setup is a little bit different, right? So the problem we're looking for is so in the context of optimal path routing. So what we are interested in are indeed the optimal path from source to destination. Okay. Yeah. And, sorry.
Yes, I just said okay. Yes.
Okay. And yeah, and I mean we talked about in the discussion. So and the setup is also a little bit different. So the properties satisfied by these other algebras are slightly more relaxed. So for instance, they don't satisfy neither commutativity nor inflation. But I guess in any case, you could still define a largest isotonic reduction, maybe with some other close from and go on from there. For instance, you could think of computing or producing largest isotonic reductions of these policy-rich algebras to reason about problems such as the termination of BGP.
Okay, so we aren't getting any questions on the Slack channel. So viewers, please send questions. So I'll ask another one. Yeah, I noticed that you can get extra, you can get sort of, let's say, unexpected routes in your solutions. So do you have a bound on the number of routes that could be produced to a fixed destination? Yeah,
so I guess that for some instances of attributes, for instance, if attributes are pairs of lengths, so pairs of two additive metrics, it can happen that you can build some very special network for which the number of dominant attributes, so the number of routes computed in a given order is exponential in the size of the network. For the examples that we gave in the paper, so pairs consisting of a width and a length, this number is only polynomial because because lengths are a minimal metric. But furthermore, we showed in our evaluation that in fact the actual number for real topologies is very much below this threshold. And but it can happen. But one thing that we can do in one of the classes of the vectoring protocols we presented is that we can trade the optimality of our scheme for the state that is kept at each node. So we'll be losing we'll be losing a little bit of our optimality, but we will gain on the complexity of the storage at each node.